For my Lab 5 video, I decided to explore the energy principle as it relates to the rotational motion of an object, a yo-yo in my case. The motion of a yo-yo falling from rest was observed and tracked via Tracker. From Tracker, a CSV file was created with the position and time values as the yo-yo fell from the full length of its string. Using what we have learned about the energy principle of a yo-yo, we treat it as a point-particle system. With Newton's second law, I constructed a Python program to recreate the yo-yo's motion. Finally, I compared the motion of my observed falling motion video and the one created in Python. I compared the position versus time graphs along with the calculated energies to determine whether the program was able to produce an accurate prediction of the motion and the system energies of the yo-yo. So again, the experiment observed the motion of a yo-yo to determine the energy prevalent in the system and surroundings. The purpose was to determine the motion and the system energies of the yo-yo, which was our system. And the results showed that the VPython model was fairly decent in predicting the motion of a falling yo-yo. The VPython model was also within 3.39% accuracy of calculating the work the string exerted on the yo-yo during the fall. Here's my tracker video of the falling yo-yo. You can see that I placed the origin of my axes at the start of the fall before the yo-yo began its descent. The video was calibrating using the diameter of the yo-yo. Even though it's not completely evident, if you look closely, there is also some motion in the X position of the yo-yo, so the motion was not just restricted to the Y-axis. Other information that I calculated was the yo-yo's mass, radius, initial and final velocities, as well as the total distance the yo-yo fell, which was equal to the length of the string to which the yo-yo was attached. As in previous labs, Newton's second law was applied in the VPython code to update the position and velocity of the falling yo-yo. In this lab, the net force acting on this yo-yo is assumed to be equal to the force of gravity. Because the yo-yo was dropped from rest, the assumption was made that if the hand produced no force on the yo-yo, then the drag or air resistance was negligible. It's important to understand the energy principle as it relates to this lab. In this lab, the yo-yo is being treated as a point-particle system. This means that the total translational kinetic energy of the system is equal to the total energy of the system. In this case, the total energy that is equal to the work done by the string in the positive y direction, plus the work done by the Earth in the negative y direction. By rearranging the equation, we can solve for the work done by the string by using knowns to calculate the translational kinetic energy as well as the gravitational work. Using the mass and the initial and final velocities of the yo-yo, the change in translational kinetic energy was found to be 0.0623 joules. The work done by gravity was found to be 5.3704 joules. Using the mass, gravitational constant for Earth, and the distance the yo-yo fell during the tracked video. These values were subtracted from one another and produced a value of 5.941 joules for the work of the string on the yo-yo. Applying these principles to the VPython code, the initial conditions were set at the beginning. These included the mass of the yo-yo, the yo-yo's radius, the yo-yo's initial position and velocity. This code was inputted into the file to create a new CSV file. In this CSV file, the position versus time data calculated from the model was written. This data was used later to compare the position versus time of the experimental motion and the model's motion. The delta t for this experiment was set low in order to create more accurate results using Newton's second law. Earth's gravitational constant is set to 9.8. The next lines show the code reading in the CSV file created from the data retrieved from the tracker video. It is used to recreate the motion of the experiment within the model in order to compare the two. The final lines show the code for how to compute the system energies involved in the experiment. In the while loop, the code updates the position and velocity of the yo-yo using Newton's second law and the fact that we assume that the only force acting on the yo-yo is the gravitational force. Finally, the point-particle energy principle is applied to calculate the work done on the yo-yo by the string. The code prints the change in translational kinetic energy, the gravitational work, and the work done by the string. This printout was used to determine whether or not the code could accurately predict the work done by the string. Now let's run the VPython code. The black ball represents the yo-yo of my experiment, and the blue ball represents the yo-yo of my VPython model. As you can see, although the black yo-yo does vary considerably in the x direction, it stays fairly constant with the blue ball in the y direction, as you can see by the chart on the right. In the model, you can see that the position versus time graph of the experiment and the model match very closely. Initially, the model slightly overpredicted the fall of the yo-yo. This could be due to small amounts of air resistance, but because the two curves eventually meet, it's more likely that this was simply a tracking error on my part. Toward the end of the time interval, the two curves diverge. This could be due to the fact that the video was tracked until the yo-yo almost came to a momentary stop at the bottom of the string. While the experiment shows that the yo-yo would have begun to ascend back into the air, which follows the motion of a normal yo-yo, the model assumes that the yo-yo would have continued to descend. Comparing the calculated energies from the experiment and the model, we see that they match very well. The printout from the code shows that the model calculated the work done by the string to be 5.1389 joules. This was within 3.39% of the experimental value calculated work. Thus, I concluded that my code was accurate enough to predict the motion and the energies of the falling yo-yo. To further this experiment in the future, I could try to calculate the rotational motion of the yo-yo by using the real system instead of a point particle system. I could also observe the yo-yo's full motion, which would involve coding for the change in direction that the yo-yo experiences. Here's a quick recap. In step 1, we analyzed the data of a yo-yo on a spring in Tracker. In step 2, we created a model of this motion using VPython. Step 3, we compared the observed motion of the system with the predicted motion of the system. And in step 4, we made conclusions about the motion and energy of the yo-yo. Thanks for watching my video.